So today we'll discuss about simple harmonic motion. Simple harmonic motion. So here we have to discuss some basic terms of simple harmonic motion. Like what is simple harmonic motion? What are the different terms required to understand simple harmonic motion? Then we will discuss about phase of a simple harmonic motion, phase of a particle which is executing simple harmonic motion. Then we will try to understand some calculation, but this is not in your syllabus, that is composition of linear simple harmonic motion, is when two simple harmonic motion are along the same line, and composition of rectangular simple harmonic motion. Then we will see what is simple pendulum, what is compound pendulum, and energy of a particle in simple harmonic motion. Okay, so let's begin our journey. What is actually simple harmonic motion? Simple harmonic motion means, let us first try to understand some examples of simple harmonic motion. Say, suppose you have a pendulum. How the pendulum oscillates? It goes towards one end, comes back, again goes towards it, and again comes back. So this motion is an example of simple harmonic motion. So what are the characteristics of it? It is to and fro motion. It repeats itself again and again. It is a periodic motion. And as it goes, see, when it goes from this mean position towards the extreme end, its velocity decreases. Okay. So we say the acceleration increases in this direction. As the displacement increases, actually its velocity decreases in this direction, or in other words we can say its velocity increases in this direction, or we say the acceleration increases in this direction. So the characteristic of this simple harmonic motion is to and fro, periodic, repeats itself, and acceleration and displacement are proportional, but their directions are different. We can take another example of simple harmonic motion. Suppose you have a spring here, and you put a load, and just you pull it by a small distance and leave it. So what will happen? This spring will execute to and fro motion. This is an example of simple harmonic motion. Okay. Suppose you have a liquid in a ink tube. This is an ink tube, and you have liquid. So if you blow air in it, okay, then what will happen? The liquid inside this tube will rise and just stop blowing the air. Then what will happen? This liquid will go in this direction, and again it comes back because the liquid difference is there. As a result, what will happen? It will execute simple harmonic motion. So these are all actually examples of simple harmonic motion. Now, let us consider the path of a particle executing simple harmonic motion along this direction. This is called the mean position. Suppose you can imagine that there is a pendulum which is oscillating. Okay. So the up to A it goes towards this direction, and up to B distance it goes in this direction. So this distance and this distance are same. What is this distance? This is the maximum distance that the particle can go from the mean position. This is called the amplitude. Amplitude. This is called the amplitude of the simple harmonic motion. Maximum displacement from the mean position. That is called the amplitude. This particular point is called equilibrium point, or this is called mean position. Mean position. So as the particle goes away from the mean position, what happens? Its velocity continuously decreases. and at this point when its velocity becomes 0, it stops and it starts coming back towards the mean position. Okay, now when it starts coming back towards the mean position, then what happens? At this point it gains maximum velocity. So when the velocity is maximum, it cannot stop here. So it crosses this mean position and goes away from this mean position. Okay. As it goes, its velocity again decreases, stops here, and start coming towards mean position. So this way the particle executes simple harmonic motion. Okay. Now, how can we mathematically represent a simple harmonic motion? Let us understand. This is a bit complex, but you can easily understand. Okay, this is mathematical representation of simple harmonic motion. Okay. So suppose let us draw a circle. The radius vector moves in this way. Suppose it is here, and it goes here, and it goes here. Okay, this is the motion of the radius. Suppose a spoke of a cycle is moving in this direction. It goes here. So the radius vector is executing a uniform circular motion. Then what is the simple harmonic motion? Suppose this is the diameter. This is the diameter of this circle. Okay. Now if you drop a perpendicular from the tip of the radius vector, what is this? This is the tip of the radius vector. You drop a perpendicular here. Okay. When the radius vector was here, the tip of the perpendicular was there. Now when it goes, radius vector goes from this point to this point, the tip goes here. Foot of the perpendicular is here. Okay. So when the radius vector goes from this position to the first quadrant, this position, the tip of the radius vector goes like this. Okay. As it comes back, suppose radius vector is crossing the second quadrant. This is first quadrant, this is second quadrant, this is third quadrant, and this is the fourth quadrant. So when the radius vector comes back, if you drop a perpendicular, here it is, here it is, here it is, here it is. So see, when the radius vector completes one half circle, the foot of the perpendicular goes up and then comes down. Okay? Now when the radius vector goes like this, you drop a perpendicular here, you drop a perpendicular here, what is happening? In the third quadrant, the radius vector covers like this, but of the foot of the perpendicular covers like this. Okay? The fourth quadrant, when the radius vector comes back to this point, the foot of the perpendicular covers like this. It goes from here, then here, then here, then ultimately at the mean position. So what is happening? When this radius vector completes one complete rotation, what is happening? The foot of the perpendicular goes up, down, down, and then up. So this motion of the foot of the perpendicular is simple harmonic motion. So mathematically we can represent a simple harmonic motion by uniform circular motion of a radius vector such that the foot of the perpendicular drawn from the tip of the radius vector on the diameter executes to and fro motion, that is simple harmonic motion. Okay. Now we'll understand some basic terms of simple harmonic motion. How to find out displacement of a particle executing simple harmonic motion. Okay. So let us, we call it displacement equation. So what is this equation? What this equation will give you? This equation will give you to find out the position of the particle at any instant of time t. Okay. So let us consider a circular motion of a radius vector. So here the particle is here. At time t is equal to 0, the particle is here. The radius vector is here. So if omega is the angular velocity, omega is angular velocity. What is angular velocity? The angle made by the particle at the center per second. Okay. So in t time, it goes from this point to this point. So what will be the angle? Per second it makes an angle omega. So in omega t time, at time t it is here. So this angle will be equal to how much? Omega t. This is the angle. Okay. Now, if you draw a perpendicular on the diameter, this is the position of the particle. Okay. This is the position of the particle. So how far it is from the mean position? It is at a distance. This is y-axis, so we can take it as y distance. Okay. Now in this triangle, if this is omega t, then this is parallel to this. So this angle will also be omega t. Okay. So this is a right angle triangle. This is 90 degree. Good. So sin omega t is p by h. What is this? This is the length of the radius vector. This is the maximum displacement, possible maximum displacement from mean position up to this point. This is called the amplitude. Amplitude is the distance from the mean position up to the extreme end. Okay. So let us say A is the amplitude. Amplitude. Okay. So in this triangle, so suppose this is A. In triangle OAP, sin omega t is p by h, OP by OA, OP is y, OA is the maximum distance, that is length of the radius vector A. So y equal to A sin omega t. This equation is called displacement equation. Why it is called displacement equation? Because if you put the value of t here, then we can find out the position of the particle. Okay. This is called displacement equation. And if you understand this, how this equation has come, we have already shown you that simple harmonic motion can be represented mathematically by the motion of a radius vector in a uniform circular motion in such a way that the foot of the perpendicular drawn from the tip of the radius vector on the diameter executes when for simple harmonic motion. So this equation actually giving us the position of the particle at any instant of time t. T is the only variable here. Okay. A is the maximum displacement, that is the amplitude which is constant for the simple harmonic motion. If it is a free motion, there is no damping, there is no external force, then A is remaining same. Now, we will plot this graph of displacement equation. Let us plot the graph of displacement equation. And I can draw this like this. Small circle I can draw. So this is t equal to 0. This is t equal to t by 4. What is t? Capital T. Capital T is the time period. What is time period? Time period means time taken to cover the complete path. So if it is a pendulum, suppose if it is at the mean position, if it goes to here, comes back, goes here and comes back here. So this is called time period. The time taken by the particle to complete one oscillation is called time period. Suppose normally we leave the pendulum from this position, so it goes towards this path, again comes back. So the total time taken to execute the entire, to traverse the entire path is called time period. Okay. So time period can be divided into, as I told you, there are 4 quadrants: first, second, third and fourth. So you can say from t equal to 0, t equal to t by 4, and this is t equal to t by 2, okay, and this is t equal to 3t by 4, 3/4 the time, and here at t is equal to t, this is the complete circle, you understand? This is 1/4, this is 2 of t by 4, that is t by 2, this is 3 of t by 4, and this is 4 of t by 4, complete time, okay. So now let us plot it. Now you will see a very interesting graph. So here you put displacement y, and here you put the angle, phase angle, or you can say time along x-axis, and displacement along y-axis. So let us say this is the maximum displacement, so this is the amplitude. So at t equal to 0, when time is 0, y equal to 0, here at t equal to 0, y is 0. So if its total time is t, then this is t by 2, this is t by 4, this will be 3t by 4, correct? So at t equal to t by 4, so this omega t will be t by 4, omega t is 90 degree, and y equal to a sin 90 degree, sin 90 is 1, so y equal to a, so at t equal to t by 4, y equal to a, correct? Now at t equal to t by 2, t by 2 means here, so this angle is 180 degree, sin 180 degree is 0, correct? So at t equal to t by 2, the particle displacement of the particle is 0, means it has come back to mean position after covering half distance here. Now at t equal to 3t by 4, this angle is how much? 270 degree, 90, 90, 90, 270 degree, and sin 270 degree is minus 1, correct? So at t equal to t by 3t by 4, this is minus 1, so y equal to minus a. So at t equal to 3t by 4, y is equal to minus a. So if it is plus a, if this distance is plus a, then this distance is minus a. And t equal to t, complete time period, then this is equal to 0 because it has come back 360 degrees. At t equal to t, this is sin 360 degree, sin 360 degree is 2 pi, any multiple of pi in case of sin is 0, so this will be 0. It goes on, okay. The particle will not stop, continuously travel like this. Now if we draw in freehand all these points, what do you see? It is a sine graph. It is a sinusoidal graph. It seems that it is like a wave. Okay. So displacement equation in a simple harmonic motion is actually mathematical representation of wave. This is mathematical representation of. So what is displacement equation? It is a sinusoidal in nature, to and fro, and it represents the wave. Okay. We have seen this graph. Now we will calculate velocity of a particle executing simple harmonic motion. Our starting point for calculating velocity, acceleration, force is same thing. That is our displacement equation. Y equal to a sin omega t. We will take this forward. Very easy, very easy. See, the displacement equation is y equal to a sin omega t. So to find out the velocity of the particle at any point of time, what we have to do? Velocity is defined instantaneous velocity, because see now the particle velocity is changing from point to point. Here we have to remember there are two velocities. One is average velocity other is instantaneous velocity. In simple harmonic motion, the velocity is instantaneous velocity because from every point the velocity is varying. It is continuously decreasing as it is going away from the mean position. Correct? So therefore, we have to find out the instantaneous velocity. Okay? Instantaneous velocity means velocity at a particular point or velocity at a particular instant of time. It is called instantaneous velocity. Instantaneous velocity can be obtained by using calculus. Okay? So, we know that velocity, instantaneous velocity is defined as dy by dt. What is dy? Small change in displacement, and dt is the time taken for this displacement to occur. So in dt time, if it covers a dy distance, then the instantaneous velocity is dy by dt. So this is nothing but, this is a differential operator, dy by dt, and y you put a sin omega t. Correct? Okay? A is constant, omega is constant. Okay? So V equal to A sin omega t, the differentiation of sin mx with respect to x is what? M sin, M cos mx. Okay? Whatever is multiplied as a multiple angle constant term, that comes out. So here it is differentiation, A will not be differentiable because this is a constant term. I have taken it out. Sin omega t, differentiation of sin omega t is omega, and sin will be converted to cos. So this is equation number 2. But it gives the velocity of the particle at time t. Very simple. Now if sin omega t is y by a, then cos omega t is how much? We know that cos omega t is 1 minus sin square omega t. Correct? So it is nothing but y minus y square by a square. Correct? It is a square minus y square by a square. So root over a square minus y square by a. So you can replace cos omega t by this term, a square minus y square by a. So velocity is omega root over a square minus y square. From this equation you can see at y equal to 0. Y equal to 0 means when it is at mean position, then the velocity is how much? Root over a square is a omega. So here velocity is a omega. Y is 0 here. When the particle is at a distance equal to the amplitude here, when the displacement is equal to the amplitude, put y equal to a here. So what is happening? A square minus a square. So this will be 0. So the velocity is equal to 0. Correct? If it is, when it is again coming back, y is 0, the velocity is a omega. At this point, y equal to minus a, doesn't matter, y square is there. So again, the velocity will be 0 here. So velocity of the particle is maximum at the mean position and minimum or 0 at the two extreme end. Clear? So this is about velocity of a particle in simple harmonic motion. Now similarly you can find out acceleration also, because acceleration is nothing but, see, I will write acceleration as f, because a we are using for amplitude. So this, what is acceleration? Acceleration is equal to the rate of change of velocity. Here acceleration is also instantaneous. Yes, velocity is changing from point to point. At every instant of time velocity is changing. So acceleration will also change. So we cannot take average. We have to take the instantaneous acceleration. So it is d by dt of velocity. What is velocity? A omega cos omega t. Okay, now we have to differentiate this part. A omega is constant, so it is not differentiable. Now differentiation of cos omega t. Differentiation of cos mx with respect to x. You have to know a little bit of calculus. So it is cos, so it will come with negative sign, m is multiplied, so it minus m, cos becomes sin. Right? Differentiation of cos mx is minus m sin mx. So here omega will come out, and this becomes minus sin omega t. Correct? So it is minus omega square a sin omega t. So this is acceleration. Acceleration is omega square a sin omega t. But a sin omega t is what? This is nothing but what? Displacement. Correct? So F equal to minus omega square into omega is constant. This is equal sign. So we can write equal sign and constant, you know, these two can be replaced by a proportionality sign. What is this negative sign indicates? Acceleration and velocities are oppositely directed. So we have got this equation, acceleration equal to minus omega square into y. Very, very important equation, very important equation. So acceleration is proportional to minus 1. In your numericals, whenever you have to prove that this motion is simple harmonic motion, always try to prove this. If you can prove that the acceleration is proportional to minus displacement, then the motion will be simple harmonic motion. So this equation we use for that. So we'll go a little bit. So this negative sign simply indicates that the velocity is measured in this direction and acceleration is measured in this direction towards the mean position. Acceleration of a particle in simple harmonic motion is always measured towards the mean position. Since these are two vectors oppositely directed, that is why this negative sign. But for the sake of modulus, for the sake of quantifying this thing, we can omit this thing. Okay. So this is very important formula. Now what we will get from this equation? Let us analyze this equation. Displacement equal to minus omega square into y. Okay. So now we are neglecting the negative sign as it indicates that two vectors are oppositely directed. Okay. So you know omega is 2 pi by t. How it is? Omega means what? The angular velocity means angle made per second. And what is t? T is the time period. So in t time period, the particle makes 2 pi angle, pi and pi 2 pi. So in t time period, the particle makes 2 pi angle. So in 1 second it will cover 2 pi by t. This is called omega. Correct? So this is this equal to 4 pi square by t square. 2 pi by t you put in place of omega. Why? So t square equal to 4 pi square y by f. So t equal to 2 pi root over y by f. Or we can say time period of a particle in simple harmonic motion equal to 2 pi root over this. Y is displacement by acceleration. Correct? So this is a formula for time period of a particle executing simple harmonic motion. Now we try to understand what is phase of a particle in simple harmonic motion. Phase means what? Direction of vibration. Where it is? Location of the particle. So phase of a particle in simple harmonic motion means What is the condition of vibration? What is the direction of vibration? Say, if I say the phase of the particle, how phase is represented? Either in terms of time period or in terms of angle. Okay. So if I say that the particle executing circular motion along y-axis and the phase angle is 30 degrees, it means what? Just complete this circle. The radius y-axis means radius vector will move in this direction. So it makes an angle 30 degree here. So put of the perpendicular is here. So the phase of the particle means location of the particle is this. But in this position the particle will come twice. So it goes up and it comes down. So what is the direction of vibration? What is the direction of motion? Direction of motion is upward. Okay? You understood, no? So either in terms of, so particle comes here twice, then the radius vector covers the first quadrant and then again it comes back to this. Then also this is the position, but here the direction of vibration is downward. Okay? So the positions are same, but the condition of vibrations are different. Okay? So phase is represented either in terms of angle or in terms of time period. If I say that the time period of a particle is 20 seconds. So at suppose at 22 seconds where the particle is. So in this case 20 seconds means each quadrant it will take 5 seconds. So it has already covered 20 seconds and 22 seconds means 2 seconds more. So suppose here the particle. So it is going up and this is the position of the particle. In 2 seconds it goes here. So the particle is already covered. So if I get the time, then also I can say what is the position and what is the condition of vibration. So phase means, phase of a particle in simple harmonic motion means position and condition of vibration and direction of vibration, direction of motion. So it can be represented either in terms of angle or in terms of time period. Okay. Now there are very famous terms normally we use: in phase and out of phase. Okay, in phase. What is in phase? In phase. Now whenever we will say in phase or out of phase, it means now there are more than one simple harmonic motion in execution. Okay. When two particles, suppose there is a particle, it is moving in this path AB, and there is another particle which is moving in the path CD. Its amplitude is different orders. Now this particle starts from this position, and the second particle also it starts from this position. The first particle goes here, second particle goes here. Okay. Same time it goes here. Again the first particle comes back to its position, second particle also at the same time it is coming to this position. Again it goes here, second particle also goes here. Okay. So both the particles are executing two different paths. They are two different simple harmonic motion, but they are moving in phase. Means if we draw this simple harmonic motion by a circular motion, okay, and this by a bigger circle because amplitude is more here. So what will happen? At any point of time, both the radius vector will have zero phase angle. There is no phase difference. Phase out of phase. What is out of phase? Out of phase means not in sync at all. Okay. See, this is one path AB, and there is another particle executing simple harmonic motion in CD. When the first particle goes here, the second particle goes here, just in opposite direction. So angle between them is all the time what is happening? 180 degree. In this case, the motion of the particle is said to be out of phase. So when the phase difference between the particle is 180 degree, means what? In the circular motion, the first radius vector small circle goes here. By this time, the second, the bigger circle radius vector, this radius vector goes here. So what is happening? The angle between them is pi, 180 degree. The particle is said to be out of phase. Okay. So out of phase means the angle between the two simple harmonic motion is 180 degree. Correct? Now the last term, epoch. Epoch means what? It is the initial phase. Epoch is the initial phase. Not necessarily the particle will execute simple harmonic motion from its mean position. Not necessarily. We can start, the particle can start executing motion from this point. Normally, we lift the particle from here and from the extreme end. So whatever be the initial angle, that angle is called the initial phase. This is called initial phase. Initial phase. So when the particle is not starting its motion from the mean position, then it has certain angle. So this angle is called the epoch. Epoch means what? Again, we will draw a uniform circular motion of a radius vector. And normally we are starting the motion of the particle from this point, but here now the particle, the radius vector starts its motion from here. This is possible. At t equal to 0, the particle is here. So what is the angle here? Some angle. Okay. So this angle is called epoch. Epoch is the initial phase angle when the particle starts its journey. When t equal to 0, whatever is the initial angle, that is called epoch. So now we covered in phase, out of phase, displacement equation. Composition of two simple harmonic motions is not there. I will check it later on. We will solve the higher advanced mathematics, mathematical numericals for simple harmonic motion. Then we will try to solve it. So there are two composition. One, when the two motions are in the same line, and when two motions are orthogonal, means mutually perpendicular. Then we have to find out superposition of two simple harmonic motion. In wave, anyway you will see in interference. Okay, in light also you will get this composition of simple harmonic motion, because waves are represented by simple harmonic motion. Mathematical formulation of displacement equation is what? It gives a sinusoidal wave. So whenever we will study interference of wave, then the composition will come. There we will discuss energy of a particle in simple harmonic motion. So what we have seen? Displacement equation, y is equal to a sin omega t. Then we have seen velocity is equal to minus a omega cos omega t. Okay, a omega cos omega t. That is equal to omega a omega cos omega t is 1 minus y square by a square. This is 2. And 3, we have seen that acceleration equal to minus omega square into y. Okay. So this happens when the particle is executing simple harmonic motion along y-axis. Okay. Because y is the displacement. Now if the particle is executing simple harmonic motion along x-axis, then this equation will be x equal to a sin omega t. So it is 1a. Velocity will be equal to a omega root over 1 minus x square by a square, 2a. and acceleration equal to minus omega square into x 3. Okay. So when the particle is here, then the force acceleration is 0, velocity is 0. Okay. So now the particle is here at a position x. So what is the acceleration of the particle? Acceleration of the particle is omega square into x. Okay. Here at this point. So what is force on the particle? Force is equal to force at the position x equal to mass into acceleration. Mass into acceleration. Acceleration is omega square x. And force of the particle at this point is 0. There is no acceleration, because if x is 0, then acceleration is 0. So at the origin, at the mean position, the force is 0. So what is the average force? Is force at origin, force at the position x divided by 2. So it is m omega square x by 2. So what is potential energy? Work done is converted to potential energy. So work equal to force into distance. So that is m omega square x by 2 is the force, into distance means x square. This is called potential energy. We can represent by U. Okay. Now, what is kinetic energy? Kinetic energy is half mv square. V square is what? Half m into v square. V square is a square omega square. Square root will go 1 minus x square by a square. So this is potential energy, equation number say 4, and this is equation number 5. So what is total energy? Total energy means potential energy plus kinetic energy, U plus K, correct? So potential energy is m omega square x square by 2 plus kinetic energy. Kinetic energy is half m a square omega square, half m a square omega square, minus this will multiply, a square cancel out, half m omega square x square, half m omega square x square. Okay. So see, these two terms cancel out. We are left with half m a square omega square. So this is the total energy. Now it is independent of x. Total energy is independent of x. Wherever the particle is, total energy is constant. Okay. So now we will plot potential energy and kinetic energy both in a graph and show you what is happening. Let us plot it here. So this is suppose the maximum energy E. What is maximum energy? Half m a square x square. Now we will plot first the potential energy. When x equal to 0 means the particle is here, U is 0, potential energy is 0, x is 0, so U is 0. When x equal to a plus a means towards this end, then U is what? Half m omega square a square by 2 total energy. So when at a position a, then this is the maximum energy. The energy is maximum. When at the other side means minus x, when the x is minus a at this point, so minus a square is also m omega square a square by 2, that is this. So when it is minus a here, then also potential energy is total energy. So what is the potential energy curve of simple harmonic motion? It is like this. So this is the U. U means potential energy of simple harmonic motion. Now let us plot the kinetic energy part. Where is kinetic energy? This. When x equal to 0, kinetic energy is maximum, correct? Because this is 0, this term is not there, so half m a square omega square. So at x equal to 0, let us mark it by black pen. So at x equal to 0, kinetic energy is maximum. At x equal to a, extreme end, there is no velocity, 0. So if you put a square by a square is 1, 1 minus 1 is 0. So what is happening? Kinetic energy is 0 here. We know that at the extreme end velocity is 0, so kinetic energy is 0. At the extreme left, minus a square is also same. So this will be 0. So now, this is the kinetic energy curve. At any point of time, if you take this point, so this is the potential energy and this much is the kinetic energy. So together will give you the total energy. So you have to remember that the kinetic energy of a particle executing simple harmonic motion is constant at every point and is equal to half m a square omega square. Clear? You know how to find out the energy, potential energy, kinetic energy, and then total energy, and we can plot the kinetic energy and potential energy curve. Now let us summarize. What we have studied here. We have studied what is simple harmonic motion, some definition of simple harmonic motion like displacement, then mathematical representation of time period, phase, epoch, in phase, out of phase, velocity of a particle in simple harmonic motion, velocity, acceleration, okay, and we have shown that acceleration equal to minus displacement, correct. Then we found the energy of a particle in simple harmonic motion. Now you come and explain. Monali, now you explain what you have understood from simple harmonic motion.
Okay. So first we started our understanding simple harmonic motion by some easy examples. For example, a pendulum which has a to and fro motion and a periodic motion. So it's in simple harmonic motion. Similarly, we have a spring which has weight below. So when the weight is put, the string stretches and then it regains its shape and size. So this is also an example of simple harmonic motion. Next, we understood some terms related to simple harmonic motion such as time period, amplitude, displacement. So basically, amplitude is the like maximum distance the particle can travel from its mean position is called the amplitude, and time period is the time taken for the particle to complete one to and fro motion. Next, we understood phase. Phase is actually the time will be given and we will be told to find where the particle is. Like it will like if there is a particle, it will be said that at 22 seconds of time where the particle will be. We know that in 20 seconds that particle will complete one to and fro motion. So at 22 seconds we can determine its position. Next we found next we understood about epoch. Epoch is the initial phase of the particle, and then in phase and out phase. In phase is when two particles are, there is no phase difference between two particles. Like if particle A is moving in if particle A is moving in x, if particle A is moving in x direction, then the other particle is also in the x direction. So these two are like in the same direction and they do not have any change, like difference in their phases. And the out phase means when the particles, they are like, for suppose A particle is moving in x direction, so the B particle is moving 180 degree, like there is a difference of 180 degree. The B particle is moving in minus x direction. Next, we understood about velocity and acceleration. When a particle, example, in a pendulum, when it goes to and fro motion. So from A, let's say this is A and this is B. So when the particle is moving here, the velocity decreases at this direction, but the acceleration increases at this direction. So by the time the pendulum reaches at the point O, its velocity has increased, so it cannot like rest there, it just moves away to the A position, and this goes on and completes one to and fro motion. Next we also got the relation that F is directly proportional to minus x, and in last we understood the energy of particle in simple harmonic motion. So a particle will have a potential energy and kinetic energy, so by adding them we will find the total energy, which will be potential energy plus kinetic energy. So at last, by calculating the potential energy of the body and kinetic energy of the body, we will find the total energy by adding them both, and by adding them we will gain E. E represents the total energy, and it will be at last m square m omega square. Just
So write above, because this is not.
I'll write it here. Okay, I'll write it here. Okay, so the total, I will just summarize it once more. The total energy of the particle in simple harmonic motion can be determined by finding its potential energy first and then its kinetic energy, and by adding both we can find its total energy, that is like held by the particle which is in simple harmonic motion. So the total energy will be determined E. The total energy will be m omega square A square by 2.
Thank you. Very nicely explained. You understood. So we will cover up the simple pendulum and compound pendulum in our next video. Thank you very much for watching.